Hello everyone, welcome to Mathematica IS. Let us discuss the 2021 group theory question of Civil Service Examination Mathematics Optional Paper 2. It says that let m1, m2, mk be positive integers and d greater than 0 be the GCD of these integers, so that there exist integers x1, x2, xk such that d can be written as a linear combination of these integers. तो ये थोड़ा सा टफर साइड क्वेश्चन था उस टाइम के लिए। हम इसको पहले प्रूव करेंगे m1 m2 के लिए, दैट मीन्स टू इंटीजर्स के लिए प्रूव करेंगे। फिर हम इंडक्शन लगा के इसको mk या फॉर एनी इंटीजर के लिए प्रूव करेंगे, एनी नंबर ऑफ इंटीजर के लिए प्रूव करेंगे। सो फॉर दीज टू इंटीजर्स we need to prove that for m1 m2 let d be the greatest common divisor of GCD of m1 m2, then there exists x y belongs to group of integers such that d can be written as a linear combination of m1 and m2, that is x m1 plus y m2. This thing we need to prove. So first of all, let us construct a set S such that it consists of elements of the form x m1 plus y m2 such that x m1 plus y m2 are positive and x comma y belongs to set of integers. Now let us prove that this set is non-empty. Since it is given that m1 and m2 both are positive, and m1 can be written as m1 is equal to 1 into m1 plus 0 into m2. That means m1 can be written as in this form, x into m1 plus y into m2, x into m1 plus y into m2. That means m1 belongs to S. Similarly, m2 can be written as 0 into m1 plus 1 into m2. This also belongs to S. That means S is a non-empty and S contains all the elements which are of this form and are positive. That means S is a subset of natural numbers. So we apply the well ordering principle. Well ordering principle. It says that a non-empty subset of natural numbers has least element. That means S has least element. Let us say this is element is x naught m1 plus y naught m2. We can say this is D. Say there exists x naught and y naught belongs to Z such that x naught m1 and plus y naught m2 is the least element of S. Now we will prove that this least element is the GCD, that is greatest common divisor of m1 and m2. So our claim is x naught m1 plus y naught m2, that is D is the GCD of m1 and m2. This thing we need to prove. So for to prove something as GCD, we need to prove three things. That if we want to prove D as GCD, that means D first we need to prove that D divides M1. Second thing we need to prove that D divides M2. Third thing we need to prove that if any other integer C divides M1 and M2, then C divides D also. That means if there is any other common divisor of an M1 and M2, then that common divisor will divide the greatest common divisor. That means D is the greatest common divisor. This thing we need to prove. First of all, we need to prove that D divides M1. Since D belongs to S, M1 belongs to S. That means both are positive. Positive, then we can apply division algorithm. Division algorithm. It says that there exist Q and R such that M1 is equal to D into Q plus R, and R is between 0 and D. Let us consider that R is not equal to 0. Then R is equal to M1 minus D into Q. From here we can write R is equal to M1 minus D into Q, and M1 minus D can be written as X naught M1 plus Y naught M2. So M1 minus X naught M1 plus Y naught M2 into D, which is equal to M1 into 1 minus X naught D plus Y naught D into M2, which is equal to R. And we know that R we have taken greater than equal to 0, and R is not equal to 0. That means R is greater than 0. And we have written in the form of M1 into some integer plus M2 into some integers. That means R belongs to S. But R is less than D. And we have considered that D is the least element of S. But here we come to the conclusion that R belongs to S and R is less than D, which is a contradiction to the fact that D is the least element of S. That means R is not equal to 0 that we have considered is not true. That means R is equal to 0. If R is 0, then M1 is equal to D into Q. That means D divides M1. Similarly, D divides M2. Same process we can follow for M2. Now let us prove third thing, that if any other integer C divides M1 and C divides M2, that implies C divides X nor into M1 plus Y nor into M2, which is equal to D. That means C divides D. Hence we have proved that D is the GCD of M1 and M2. That D divides M1, D divides M2. If any other integer is a common divisor of M1 and M2, then that common divisor divides the D. That means D is the GCD of M1 and M2. And D is equal to X nor into M1 plus Y nor into M2. And X nor and Y nor are two integers. That means the GCD of M1 and M2 can be written as linear combination of M1 and M2. So we have proved for the two integers M1 and M2 that GCD of M1 and M2 can be written as linear combination of M1 and M2. Now to expand this or extrapolate this to the k number of elements of k number of integers mk. So first of all, to extrapolate this to k number of integers, we need to prove that GCD of m1, m2 and m3 is equal to GCD of GCD of M1, M2 and M3 outside. If GCD of M1 and M2 is P, then GCD of P comma M3 here. M3 is equal to GCD of M1 comma M2 comma M3. This thing we need to prove. So let us assume that GCD of M1 comma M2 comma M3 is equal to D, and GCD of M1 comma M2 we have assumed that it is P, and GCD of both these is equal to, let us assume that it is D, and now we need to prove that this D is the GCD of M1 comma M2 comma M3. So let us assume that GCD of P comma M3 is equal to D, and what is P? P is GCD of M1 comma M2. Now we will prove that this D is GCD of all three integers M1, M2 and M3. Since we assume that D is a GCD of P comma M3, that means D divides P and D divides M3. D divides P, that means D divides GCD of M1 comma M2. That implies D divides M1 and M2, and D divides M3, that means D divides all M1, M2 and M3. Now to prove D as GCD of these three, let us assume that C be another common divisor of M1, M2 and M3. Since C divides M1, M2, that means C divides P, GCD of these two, and C divides M3, and GCD of P and M3 is D, that means C divides D. Hence we have proved that D divides M1, M2, M3, and if any common divisor of M1, M2, M3 is C, then C divides D. That means D is equal to GCD of M1, M2 and M3. Hence GCD of M1, M2 and M3 is equal to GCD of M1, M2 and GCD M3. This we have proved. Now we will apply induction. Induction that, let us, if M1, M2 and M3 are three integers, then GCD of these three integers can be written as linear combination of x1 M1 plus x2 M2 and x3 M3. How can we write this? GCD of M1, M2 and M3 is GCD of M1, M2 and GCD M3. So this is one number, let us say it is D, and this is another number M3. GCD of two number can be written as linear combination of x1 D plus x2 M3. Now D is GCD of M1 and M2. It can be written as a linear combination of M1 and M2. So x1 x2 M1 plus, sorry, y2 M1 plus y3 M2 plus x2 M3. So we open this bracket, x1 y2 into M1 plus x1 y3 M2 plus x2 M3. That means it is a linear combination of M1, M2 and M3. Hence D can be written as a linear combination of M1, M2 and M3. We have proved for three integers. Similarly, it can be GCD of M1, M2, dot 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 mk can be written as GCD of m1 dot dot mk minus 1 and mk GCD of. So we apply similarly. This can be if by induction that it is true that for any integers less than k, this is true. That means these integers, if the number of integers is less than k, they can be written as linear combination of themselves. Their GCD can be written as linear combination of themselves. Then we will add another number mk, and we will this can be written as a linear combination because it is less than k, and we will apply the for GCD of 2 for this. Then we will get our desired result, that D is equal to x1 m1 plus x2 m2 plus dot 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 xk mk. This was asked in 2021. It was a quite tough question for that time. Thank you guys. You can subscribe and like and share this video to other aspirants for their help. Thank you.